If you have ever worked with electronics, you've likely heard about decoupling capacitors. But do you know why they are so important? In this video, we will delve into them and their significance in electronics design. In electronics, different parts of a circuit can create noise or electrical disturbances that can affect the performance of other parts of the circuits. This noise can be caused by various factors such as switching of transistors, voltage spikes, electromagnetic interference, and so on. Decoupling capacitors are used to suppress this noise by providing a low impedance path to ground for high frequency noise. These are two circuits to demonstrate the presence of noise. First, an LM7805 voltage regulator, which receives a voltage and stabilizes it to 5 volts DC. And with this 555 timer, generating a square wave at 123 Hz, which is considered low frequency. For the input of the regulator, I'm using a switching mode power supply adjusted at 9 volts DC. By looking into the output with the multimeter, everything appears normal, with an average output of 5 volts. If we look with the oscilloscope, indeed it appears around 5 volts. Good. But if we look close there, the line looks fuzzy. This is electrical noise, mainly generated by the power supply, but also by the regulator itself, internally switching at high speed trying to stabilize the output voltage. This noise includes a ripple, seen as a high-frequency AC component superimposed on the DC signal, which can cause problems in certain applications, in this case more than 900 millivolts. If we add some load at the output, let's say this LED with a resistance, guess what happens? Ouch! The regulator gets more stressed due to the load, and the output noise goes even higher, almost 2 volts peak to peak. This noise is also getting back to the power rail of the circuit. I'm enabling the second channel of the scope to see both signals. See the blue line, how the noise increases as I connect the LED, which means that other components on the same circuit will be affected as well. The datasheet recommends adding one capacitor of 0.22 microfarads at the input, and an optional one at the output. The first is the decoupling capacitor because it decouples or isolates this component from the rest, in this case from the power supply. I will use this film capacitor of 0.33 microfarads, which is the closest one that I have. Oh, perfect! The new readings of the peak-to-peak noise is around 150 millivolts. We have an improvement here. Great. Now let's analyze the 555 timer. The signal looks like a classic square wave. But if we zoom in, we see this spike on the left, and lots of noise with it. For this circuit, the input is 9 volts. The peak is more than 6 volts. That's 54%. For reference, it is too much. I'm adding 2 capacitors at the power lines of the integrated circuit to see the effect. Why 2? And how did I know the values of each of them? Well, because they are prescribed in the datasheet of the manufacturer. The final square wave looks much cleaner. The readings this time for the noise amplitude is only 400 millivolts. Compared with the previous one, it is way lower. Perfect! What if we connect the output of the regulator to power the 555 timer? We do this by connecting the ground line and then the output of the regulator, this pin 3, to the power line of the 555 timer. That means that we are accumulating the power supply, the regulator, and the 555 timer in series. And actually, this is a common array for many circuits. The shape of the square wave reflects the accumulated noise from the power source and from the regulator. So imagine having this kind of behavior in more complex circuits. This is a ripple and noise. Notice this tilted section of the wave. That's not right. We can measure more than 900 millivolts. This is 20% of 5 volts. Now let's go ahead to add the decoupling capacitor to the input of the regulator. Now we have like 500 millivolts of peak-to-peak noise. Things are getting better. That's good. Now adding the first of the two decoupling capacitors of the 555 timer. First, with 0.1 microfarads, or 104 code for a ceramic capacitor, which should remove higher frequencies. This gives like 140 millivolts for the noise. Now, adding the electrolytic capacitor of 1 microfarad. This one should remove the lower frequencies from the noise. This one is only helping to fix the left side of the shape, but not for reducing the overall noise. Anyway, we'll leave it as it is prescribed by the datasheet. Our final signal is squared and flat at the bottom and at the top, and not that thick. And the final noise gives 140 millivolts, equivalent to 2.8%. That's a more acceptable value. Not bad. But what if we need a cleaner output signal? First, let's remember that a breadboard is not the best way to measure and eliminate electrical noise. However, there are several techniques that can be used, but those depend on condition of circuit. That includes frequency, amplitude, power, peak amplitude, external interference, radio frequencies, nominal voltage, tolerances, cost, and many others. But those are not covered in this video. Okay, now we have a practical idea of why decoupling capacitors are so important. I hope you liked this video. Thanks for watching. Knock knock. That's 50. That's good. Good. Millivolts per. But what if